Now going to talk a little bit about manometers, what they are and how they work. Now, a manometer is actually called a U-tube. Now, this isn't the U-tube that you're watching this video on. Obviously, the name U-tube comes from the shape of the U-shaped tube. Duh. Now, how does this thing work? Well, I call it the push-a-push war. Now, you can imagine two sumo wrestlers, and basically, I'm not a sumo wrestler, but the way it works is you take a ring, a circle on the ground, and you try to push the other person out of the ring by using your body. That's it. It's a push-a-push war. Now, I have here a liquid in a tube, and I have two pressures, pressure 1 and the pressure from the atmosphere. Now, as long as pressure 1 and the pressure from the atmosphere are both pushing equally at one another, there is no difference in the height level of the liquid. So at this point, the two pressures are equivalent. If, though, one pushes harder than the other, so let's assume that pressure A is 750 millimeters of mercury. That's the atmospheric pressure. We got that from our barometer. And now look at what happened. The atmosphere, right now they're even, and if this hand is going to be the one that's the atmosphere, if this is pushing 750 millimeters, well, it's in the graphic, it pushed this one down and this one went up. So clearly, the atmosphere is a higher pressure than pressure 1. Now, how much higher? Well, the way these actually work is there would be a measuring instrument, like a meter stick, right here. And we could actually get the height difference. So from the push-a-push war, whichever is the higher one is the lower pressure, or whichever is the lower down. So this is lower than here. Lower down is higher pressure. So if I were to measure the height difference between the top here and the bottom here, that height difference is 130 millimeters. Now, did we say pressure 1 was higher or lower? It's lower. So it's lower than this one by 130 millimeters. So if we simply subtract those two, we would get the pressure in gas 1. And it would be, well, somehow this got a little messed up on my graphic, because if we assume that pressure 1 is 750, then we know that this one, the higher pressure, is 130 millimeters higher, would be 880. Let's go the reverse way for a second. Now, if we look at this situation, we can see that the pressure here is pushing down more, winning the push-a-push war. So this is the lower pressure. How much lower than the 750? Well, 130 millimeters difference. 750 minus 130 is 620 millimeters. We'll practice some more of these, and I think you'll find that manometer problems are really very straightforward. So let's look at this situation here. I've got now a confined bulb. That's what the pressure in the bulb is, because I'm measuring the pressure of a closed system of gases. That's what a manometer would be used for. At this point, the pressure from the atmosphere and the bulb are the same, and they're at the same level. That's what we can tell so far. So if pressure A is 750 millimeters, then pressure B would be 750. Now I've changed the situation so that the atmosphere is pushing down more than the bulb. So the bulb must be lower pressure. How much lower? Well, the difference in the height between these two. So if the height difference is 130 millimeters, if the atmosphere pushes down 750, by simply subtracting those, I will get the lower pressure, the pressure of the bulb, to be 620 millimeters. Let's try this one. What if we have everything reversed? Who's winning the push-a-push war? Well, the bulb is now winning, pushing down farther, harder against the atmosphere. So if we know that the pressure of the atmosphere is 750, and we know the height difference is 130, the pressure in the bulb must be 130 millimeters higher than the pressure of the atmosphere. So in this case, I will add the two pressures up to find the pressure inside my bulb is 880 millimeters of mercury. That's all you have to do to figure out a manometer question. Now, I want to spend a little bit of time talking about some what are called Boltzmann distributions to understand what these things are. So I'm not going to read this all to you. I'll give you, I guess I'll paraphrase a little bit. So it says basically when you have gases at a certain temperature, they're not all moving at the same speed. That's basically what this says. So let's look at this in some detail. So we're looking at nitrogen molecules. So if I'm at 300 Kelvin, oh, that's just about room temperature, then it says most of the molecules are going to be right about this speed, 480 meters per second. Some of them will be a little faster at 1,000, some slower, but that's an average peak. Now, as I heat up this sample of gas, notice that fewer and fewer molecules get to the same velocity. In other words, in order to get to 600 Kelvin, some of the molecules are going to be very, very fast moving and others not so fast. And the higher temperature you go, the lower the curve gets and the farther to the right it gets. So summarizing that, if we were to look at number of particles of oxygen at 10 degrees Celsius, they're going to be all pretty closely moving at the same speed. At 50, they start to spread out a little bit more, and at 100, they spread out quite a bit. I like to use the analogy of education. It's very easy to get everyone to a, let's say, 6th grade reading level. It's relatively easy to get the majority of people to that level. This might represent high school diplomas, a little bit harder to get people to all graduate, and this might mean college diplomas. You can see some people have lots of education and some, well, they have easier majors, I suppose, because they're way down here. Not sure if that helps, but that's a Boltzmann distribution. So one way to look at this is the same gas molecules at different temperatures. The higher the temperature you get, the fewer the molecules you will have at that particular temperature. Another way to think about this is if I have a pan of water at room temperature and I put it on a stove and turn on the oven, turn on the flames, I can probably get that water, most of the water, to raise 5 degrees Celsius. But if I try to get all of that water to raise 50 degrees Celsius, it's going to be much harder for me to do. Some of the molecules will get very hot and some won't be quite as hot. The other way we can look at this is look at number of particles versus speed of the mass of these molecules. Now, carbon dioxide weighs 44 grams per mole, nitrogen weighs 28, and hydrogen 2. So what it says is, at the same temperature, you're going to have the big molecules moving slower, and the lighter molecules, like hydrogen, will move on average at a faster temperature. That's what this graph is trying to tell us. If we were to look at and measure, let's say, the molecules' average speed or kinetic energy in a glass of iced tea versus hot tea, we'd find that most of the molecules in the iced tea would be closer to the same speed, where in the hot cup of tea, you'll have some slow-moving molecules and some really hot-moving molecules, but you will not get as many molecules at that same velocity. All right, let's go back to our manometer problems. You'll have a homework sheet, looks something like this, to work out. Now, what's different about these? Well, what's different is sometimes I give you a unit of atmosphere, sometimes kilopascal, and sometimes millimeters. So we're going to have to convert those a little bit. So let's go ahead and look at this question together, number 2. So we'll go to that problem. I believe this is the problem here. So the first thing you have to do when looking at a problem like this is figure out what unit you need everything to be in. Now, the fact that the unknown is in millimeters, my preference would be to convert this to millimeters and this to millimeters. If we do that, it's going to make things a lot easier for us. Next, let's figure out who's winning the push-a-push war. Is the atmosphere winning or is the bulb winning? I heard several of you say the atmosphere. Why do you say that? Because it's a bigger number. Well, you're right, but not really. You're correct in that the atmosphere is the higher pressure based on the height difference. It pushes down more, so therefore it is the higher pressure. But do not, I repeat, do not just assume that 112.8 is a larger number than 0.78, and that's why it's the bigger number. Because you're comparing apples to oranges, kilopascals to atmospheres. You must have the same unit to make that comparison. But even without knowing the numerical value, just looking at the height differences, the atmosphere is the bigger pressure. So now what I'm going to do is, my first step says decide which pressure is bigger. And well, we've decided that it's the atmosphere is bigger based on the push-a-push war. Next, it says convert all numbers to the unit of the unknown. The unknown in this case is millimeters of mercury, so that's what I need to get to. So I have to do some conversions. Perhaps you remember 1 atmosphere is equal to both 760 millimeters of mercury as well as 101.3 kilopascal. So I'm going to set up my dimensional analysis. 101.3 kilopascal is 760 millimeters of mercury. Kilopascal cancels like that. And if I solve that, I will have a unit of millimeters of mercury, 846 millimeters. Now I must also do the same thing for the bulb pressure in atmosphere. I'm going to do that next. So we've got 0.78 atmospheres, and we said 1 atmosphere is equal to 760 millimeter. Atmosphere cancels like that, and we're left with a pressure of 593 millimeters of mercury in the bulb. Now it's obvious if we compare 846 millimeters to 593 that the bigger pressure was indeed the atmosphere. Next, I have to use this very fancy, very difficult equation to memorize, learn. Big equals small plus height. I don't know how students can mess that up. I hope you wouldn't say big plus height equals small. That doesn't make any sense. The big pressure is equal to the small pressure plus the height. So we're going to use that formula. Now, in this case, I'm solving for height, so I might want to rearrange that equation. I'll go ahead and do that right now, so that height is equal to big minus small pressure. In this case, the height will come out in millimeters. The big pressure was 846 millimeters of mercury, and I'm going to subtract from that the small pressure, 593 millimeters. At this point, I type that in my calculator, and I get my final answer. The height difference that I would expect in this case should be 253 millimeters of mercury. I hope that makes sense. If you have questions, please send me an email and we can discuss it further. Thank you. Good luck. Stay healthy.